Hi everyone, welcome back. We're going to continue with text analytics and focusing on SVD. So previously we learned about SVD being a very powerful generalizable technique. So today we're going to look at what are the other uses of SVD, such as doing dimensionality reduction, and we'll also look at a case study of how we can use SVD. So let's first do a quick recap of what we have learned so far about SVD. So we decompose our original matrix A into smaller matrices U, V, and lambda. And in the context of text analytics, we have the U matrix, which is a document concept similarity matrix. V is a term concept similarity matrix. And also lambda, which is a diagonal matrix with the concept strength as the values. So the matrix U and V actually have some interesting relationships to our original document term matrix A. So specifically, if A is the document term matrix, then AA transpose is the term-to-term similarity matrix. And similarly, AA transpose is the document-to-document similarity matrix. So by computing SVD on our original matrix A, we get the matrix V. And very interestingly, that actually contains the eigenvectors of A transpose A. So similarly, U contains the eigenvectors of AA transpose. So what does all these mean? So it means that SVD is closely related to PCA, or principal component analysis, a very popular dimensionality reduction method. Because in PCA, we need to compute the eigenvectors of A transpose A. And by multiplying A transpose A is actually not a very good thing to do, because it can lead to loss of precision. And in other words, SVD allows us to compute the eigenvectors needed by PCA without having to actually materialize or explicitly multiply A transpose A. If you want more information about SVD, PCA, and also their relationship, I highly recommend you check out the link below and also the excellent book. So another way to interpret SVD is that SVD can help you find the best axes to project on. So best here is characterized by how well it can minimize the sum of square of projection errors. So in other words, SVD can help us find, let's say, the first singular vector v1. And v1 will be pointing along the direction of the data that has the greatest variance. And the variance would be captured by the lambda matrix. So specifically, let's say for v1, which is the first singular vector, its variance, or the spread, would be captured by its concept strength, which is 9.64 in the lambda matrix. So in other words, if we multiply U and lambda, those two matrices together, so it actually gives us the coordinates of the points on their projection axes. In this case, like v1 and v2. So by understanding this interpretation that SVD is actually helping us find the best axes to project our data on, now that we can actually figure out why we can use SVD to do dimensionality reduction. Right? For example, instead of, say, two concepts, as in what you're seeing on this screen, we can actually use the values in lambda matrix to guide us. For example, if, say, we have a gigantic matrix with like millions of rows, like billions of columns, right? So how do we compress this, or how do we extract the most important, most relevant concepts or themes in this data so that we don't need to store the whole matrix? So the way that we can use the lambda matrix is we can look at the strength. So remember that these values in the lambda matrix, they are sorted. So the one with the greatest strength is at the top left. The one that's the smallest strength is at the lower right. So what that also means is we can actually start setting the values that are the smallest to 0, like going from the bottom right and then gradually going to the top left, right? So that means however many concepts that we want to keep. So those are the diagonal entries that we want to still keep their original values. And all the other diagonal entries, we just set them to 0. And by setting those to 0, what that also means is we're essentially zeroing out the corresponding vectors. So if you do the multiplication, you will know that we don't care about those vectors anymore, because as long as the values, the concept values in the lambda matrix is set to 0, the other ones, we don't really care what they are. So essentially, that means we're cutting out all those columns, those rows from our U and V matrix. If you multiply those three truncated matrices together, you will end up getting a matrix that has the same dimensions as our original data matrix. But you will know that here on the lower right, so all those non-zeros in our original matrix now become zeros. So that is how dimensionality reduction is done. So by setting the concept to 0 that we don't really care about, essentially removing information in our original matrix that are not as important, and essentially compressing our data, throwing away things that we may not care about so much. So the time complexity to compute SVD exactly is big O n m m or big O n n m, so whichever is smaller. But in practice, it's very rare that you want to solve this exactly. And in practice, often instead of asking for finding all concepts, which is equal to rank of the matrix, often we say, for the million times billion matrix, maybe we only want the top 50 or top 100. And in practice, that's already probably more than enough. Right? So imagine, let's say you are Netflix and you want to find out how many groups of users there are. Maybe a couple hundred is already more than sufficient. So what that also means that instead of computing all the singular vectors, you may only want the first k singular vectors. So these would be much faster to compute. So and also, if your matrix is sparse, in practice, most likely it is, that means a lot of zeros, that is even faster to compute. A very nice thing about SVD is because it's such a powerful and generalizable technique, you don't really need to write the algorithm yourself. So it's available in almost all linear algebra packages. So that means you can just use them. So now that we know how SVD works, and also numerically we look at a few examples, so let's look at some case study. For example, how we can do queries using LSI or using SVD. Right? For example, let's say going back our documents and terms context. So how do we find documents with the word, say, data? And if you may recall from very early on, our main idea is to first try to map our data query, right, our query consisting of one word data, to map this into the concept space. Right? So how do we do that? So first, we would want to represent our query, the word data, as a vector. So essentially putting it into the vector space model. So that means now we have 5 words, right? So we would set the first entry to 1, right, for data, and then all the other entry to 0. So that means I have a 4-dimension vector. And to map this vector or our query into the concept space, all we need to do is to do the inner product, so or cosine similarity between our query vector q and also each of the concept vectors, like v1 and v2. So that means q.v1, we have one value, and also q.v2, another value. Right? So in mathematical notation, that means q times v, and then we have the q concept vector. Right? And then below on this screen, you'll see that now we have the query mapped to concept space, so 0.58 and 0. So what that means is now the query data or query vector, and it is strongly associated with the CS concept. So a related question, so how would we handle the document, let's say, that contains the word information and retrieval? So actually using the same approach. So we'll also first convert our document into vector. So again, 5 words, so dimension equals 5. And we set the entry for information and retrieval to 1, and then all the other entry to 0. And we'll do the same thing. We do a dot product. So that means our document times our V matrix, and we get the document concept vector. So again, here we will see that we have the string for 1.16 for CS concept and 0 for the other medical concept. So the important observation here is that we started off with the query, which contains only one word, data. However, by expressing everything into vectors, including the documents, all the documents, and also mapping all of them into the concept space, so now we can actually query or find all these documents that may not even include the word data, as in the example shown below. So our query contains only data. It doesn't contain information and retrieval. But by mapping that query vector into concept space, now we have the vector like 0.58, 0, that is association in terms of the CS concept. And we can use this notion. Now we can pull out all the documents that are strongly associated with the CS concept. So as an example below, even though a document do not contain the word data, we can still get it. So in this video, we'll look at SVD's other application, such as doing dimensionality reduction by simply zeroing out the concepts that are less important, and also how it can help us with retrieval, such as finding documents that may not essentially contain the word that we're interested in.